Hi, so today let's start the chapter 2 of the Wainwright's book. It's about basic tail and concentration bounds. And today we're gonna talk about section 2.1. The first part of this subsection is about Chernoff and sub-Gaussian. So the first part is from Markov to Chernoff. It gives you the motivation about the Chernoff bound. It comes from the Markov bound, and Chernoff bound is widely used in the proof of some concentration inequalities. This is the first part, so let's begin. We all know the Markov inequality from the probability course that if the random variable x is non-negative and it has a finite mean, then we have this probability. It's a kind of concentration. That means for a given positive number t, the probability that x is larger than t must be less than some value, and when t comes to infinity, this value comes to 0. So this inequality tells you that when you give a range of x that is not so large, given some range of x, it must be located in a range, then this probability must be less than some value. It cannot tends to some, when t comes to infinity, this value tends to also a 0. So this probability means it bounds some so large value of x. This is the Markov inequality, and we all know the Chebyshev's inequality like this. It uses the second order moment of variable x. Here it says the variance of x over t squared. These two are all concentration inequalities that guarantee x is close to its mean, which also means x cannot be too large. Not cannot be too large, but the probability tends to 0. It's an improbability way. So this is about these two inequalities. And we can make some extensions to Markov inequality like this. If here you apply this random variable, you apply x minus mu, and absolute value of this, the k square of this, tells that this inequality comes from that. If you write here like x minus mu k, the order is k larger than tk, you get this. So this is equivalent to this probability. So you get different orders of x minus mu. So you may think that if this procedure can be applied to some functions other than the polynomials, so an intuitive way is to consider the exponential function. So here, the author says that the random variable, if it has a moment generating function near the neighborhood of 0, so which means in this neighborhood, this random variable x has infinite order of moments. It exists infinity moments of infinity moments. So this function phi lambda exists. We apply Markov's inequality to y, and we get this inequality. So here, since this is the moment generating function here, it gives you a parameter named lambda. We can choose the value of lambda, although this function is satisfied whatever the value of lambda is. So optimize our choice of lambda, get the tightest result, which is the so-called Chernoff bound, like this. Here the author takes the log, and we find the minimal value of this when lambda belongs to this range, which guarantees that the moment generating function also exists. And here you may have a question like this. The moment bound 2.3, which use the value of some polynomial-like forms. This bound is never worse than the bound used by this moment-generating function. So why we still use this Chernoff bound but not those polynomial bounds? That's because the Chernoff bound is most widely used in practice, and it's somewhat, ease of manipulation. So manipulating moment-generating function is more ease. That's the reason why we tend to use Chernoff bound more than that of polynomial bound. And indeed, a variety of important tail bounds can be obtained as some particular cases of this Chernoff bound. So anyway, in practice, we always choose the Chernoff bound, which is ease of manipulation than those polynomial bounds. And let's come to the next part about the sub-Gaussian variables and Hofstadter bounds. So what's the definition of sub-Gaussian? Intuitively, it comes from the Gaussian random variables, so we want to find the tail bounds of the Gaussian variable. So here the author gives the example of 2.1. It gives the Gaussian tail bounds. Here x is the Gaussian random variable, and by some straightforward calculation, using the Chernoff bound, we get this inequality. So the upper deviation inequality looks like this. The probability that the random variable x larger than its mean value plus some positive t must be less than this. And let me see. This bound is sharp up to polynomial factor corrections, as shown anyway. So motivated by the Gaussian random variable, we get the sub-Gaussian, the definition of sub-Gaussian. So if the random variable x satisfies this condition, that if there exists a positive number sigma such that this is satisfied, this is motivated or driven by the property of tail bounds of Gaussian random variable like this. So if this inequality is satisfied, then we name the random variable x as the sub-Gaussian with sub-Gaussian parameter sigma. And with this definition and some calculation, we get the concentration inequality for the sub-Gaussian random variable. So here, the definition tells you that the sub-Gaussian random variable satisfies this inequality, and by symmetry, the probability that s must be less than something also satisfies the same inequality. So you combine these two subparts and get the concentration inequality, the two-sided concentration inequality like this. This is the direct property of the sub-Gaussian random variable. Here are some examples of sub-Gaussian variables, and of course they are non-Gaussian, and the writer gives you the sub-Gaussian parameters. Example 2.3 is red matrix variables. The red matrix variable will be used later to derive some bounds for like, let me say, the how to say, like risk minimization schedule. In those settings, you may use these red metric variables or some other methods like chaining, blocking to bound the results. Anyway, so the definition of a red metric variable is that it takes a value of negative and positive 1 with equal probability. So this random variable is sub-Gaussian because we can write this equation like this. So we need to verify this definition. Since the mean value of this red metric variable is 0, so we write it like this. We calculate the expectation of this and by some Taylor expansion and combine this and to get the final result using the definition of E, we get this. So this shows that red metric variable is the sub-Gaussian. Example 2.4 is important because it tells you that any bounded random variables are sub-Gaussians. So this proof is interesting because it makes an independent copy of a variable, and here the proof can follow up. This is very important because later many useful proofs will use this technique, like getting an independent copy of the original random variable, and by some manipulation, and we can get the final results. So here the writer gets an independent copy of random variable x, which is assumed to be 0 mean and bounded on this interval. So here the writer incorporates the x prime like this. So, and he writes this inequality. This follows from the convexity of exponential and Jensen's inequality. You write these two terms like you perform the E and lambda, the power is lambda times x minus this expectation, and you write it as E power is lambda x, and another term like negative, the power is negative the expectation, and you write it together, and finally you can get this. This is not hard if you learn some course like convex optimization. And how do we manipulate this term? So since the writer lets another random variable named this red metric random variable, as we have talked in example 2.3, then the distribution of this is the same as this, so we incorporate this red metric variable. So why we introduce this random variable, this red metric random variable to the proof of this, the property of bounded random variable? That's because we can apply another inequality here. So this result follows from the property of red metric random variable, since we apply this, it's applied conditionally with x and x prime held fixed. So if you fix x and x prime, and this inequality directly gets from the property of Rademacher variable. So finally, since this is bounded, X is bounded, we can guarantee the final result that the bounded random variables are all sub-Gaussian with parameter at most b minus a, but this result can be sharpened in exercise 2.4. But anyway, the result is important that every bounded random variables are all sub-Gaussians. So here the writer gives you the remark that the symmetrization argument technique is important in the proof of some results. So this is very useful in variety of contexts, which will be seen soon in later chapters. Just as the property of that Gaussianality is preserved by linear operations, so is the property of sub-Gaussianality. So we have two independent sub-Gaussian variables, then the sum of them, also the difference of them are all sub-Gaussians with this parameter. So finally, it comes to the Hofstee bounds. This is very popular. So if you suppose that we have n random variables which are independent and all has different mean value and different sub-Gaussian parameter, then the summation of them are also sub-Gaussian like this. So you can get this Hofstee bound like this. So since sub-Gaussian is somewhat technical, so the easier or the specific circumstance is that when xi are all bounded on some intervals, then we apply this to the Hofstee bound and get this bound. This is the direct use of Hofstee bound, and it's the use of Hofstee bound. Finally, let's talk about theorem 2.6. These are some equivalent characterizations of sub-Gaussian variables. Here the author lists 4 equivalent forms. The first is the definition, like this, and the second is that if the random variable can be bounded by the Gaussian random variable like this, then this random variable is also sub-Gaussian. And form 3 is about the moment conditions. So the even moments of x have to be less than some terms, and the last condition, the last form, equivalent form, is that if you get the expectation of this, so this if this is satisfied, then it's also a sub-Gaussian variable. And we can briefly talk about the proof of these 4 equivalent forms. So the proof is somewhat technical, but if you follow the proof of this theorem, it will be helpful. So let's talk about this together. Let me see. 2.4. Okay, Appendix A. So the writer established the equivalence by this step. So the first implication is from 1 to 2. So the first step is that if since this theorem says any zero mean random variable x is the random variable x is zero mean. So if when the implication 1 is satisfied that the x is sub-Gaussian with this parameter sigma, then we can claim this. So that's what we're gonna prove. Then x is measured by z or dominated by z with constant c. So how to prove that? On one hand, by the sub-Gaussianality of x, we have this inequality for t larger than 0. And here it also uses the Mills ratio, which will be shown in exercise 2.2. Then we have this ratio, this bounds, and combine these two. Not combine, let me say. We have to, to divide this proof into two cases. The first case is that when t is less than 2 sigma, then the probability that the random variable z is larger than t equals to is larger than this. Since t is larger than 2, t is smaller than 2 sigma, so the later probability is less. So we use this. Let me see. Z larger than 2 sigma, so we apply 2 sigma to the inequality 2.53, and we get this result. Then we can conclude the results. And the second case is that if t is larger than 2 sigma, by combining the Mills ratio and the sub-Gaussian tail bounds, also making a substitution, then we get this. So this term here, the exponential over this is less than this. So this is intuitive by some inequality tricks, and the last step follows from the numerical calculation. So let's make the brief conclusion of this implication. Like the author firstly tell apart or split this proof into two cases. The first case is a direct use of the Mills ratio, and the second case is somewhat sophisticated by making some substitutions, the sub-Gaussian tail bounds, the Mills ratio, and also by some inequality tricks and numerical calculation. And the second implication is driven by calculate the even order moments of x, and by another definition of expectation, or the equivalent way to calculate the expectation of the non-negative random variables, we get this, and equivalently this. So under the assumption that the form 2 is satisfied, then we can get this inequality. So since we have known the polynomial moments of z, which is normal, the zero mean random variable, Gaussian random variable z, and finally we can get the results that the form 3 is also satisfied. This is intuitive. And from 3 to 1. Firstly, we write this based on Taylor expansion of exponential function, and also apply our assumption that 3 is satisfied, then we get this. If x is symmetric around 0. So what if x is not symmetric? So this is important and can provide us with some intuitions in providing different circumstances like, well, if x is not symmetric, the even moment order of x is not 0, so how can we drive the conclusion? So here it gives you a very important trick like Cauchy-Schwarz inequality. This is important, like the author writes the even order like 2k plus 1. Use the Cauchy-Schwarz inequality like this. So the step 1 directly follows from the Cauchy-Schwarz inequality, and then we can calculate, because we've already have the even order value of lambda x, like say 2k and 2k plus 2. Then by some reformulation of the Taylor expansion, we get this inequality. So we only need to calculate this by applying inequality 2.1 to C. Then we can easily drive our conclusion, which establishes the claim. And let's get some the equivalent of 1 and 4. From 1 to 4 is easy because this proof is intuitive. Like, first of all, here the author used s. S means lambda here because the author wants to tell about different notations. So since the form 4 is that this inequality satisfies all lambda non-negative and less than 0. When lambda equals to 0, it is obvious. So when s belongs to this range, this interval will begin from the sub-Gaussian inequality as stated in the inequality 2.1 to a, and multiply both sides. So why we multiply both sides by this? Let me see. Anyway, so the author multiply both sides with this and then make some integration like this. Make some integrate both sides, and let me see, by some calculation turning to the left hand side. Okay, the left hand side, turning to the left hand side from face x, we have all right. Let's look at this inequality. We get this inequality, and the left hand side of this inequality gives you this result, and the right hand side gives you this equality. So we can take expectations with respect to x. Then we get this result. So take expectations with respect to x. Let me say so we want to conclude this result, expectation of this. So let me see, expectation of this. Here, the left hand side. So expectation of this. Where does it comes from? Let me see. I sub-Gaussian equality multiply get this. Equivalently, the left hand side equals to this. For fixed x, this satisfied, and the right hand side satisfies this. And take expectation with respect to x. So take alright. So take expectation with this. So here it has this. So that's also the reason why we have to multiply both sides by this term, because here we can get this results. So this multiplication is driven by this, so that we can get the final result here. The expectation of this is less than this. This is the multiplication term, so the inverse is here, and it's less than the right hand side, where if you do the integration, we get this. So we write this term here, and we get this final result. This is the proof from 1 to 4. So finally we get the proof and implication from 4 to 1. Here, the author applied this bound. We will talk about this bound in details later, but firstly, assume that this bound is correct. Then, we apply this bound with u equals to this and take expectations. We can easily get this, which is valid whenever s equals to this value is less than 0. Let me see. Yeah, here is the direct apply of this bound and taking expectations. We note that this satisfies for all s belongs to this interval. So whenever lambda satisfies this, s is less than 1 over 2. So we conclude the result for all the absolute value of lambda is less than this. So what happens when the absolute value of lambda is larger than 2 over 3 sigma? So the author applied another inequality named the French-Young inequality, which used the direct proportions of conjugate duals. So we have the function and the conjugate dual, then this is satisfied. So the author applied this inequality with different value of u, v, alpha, and specially chosen constant c. Then we get this. So the first is by French-Young inequality, and the second is valid by using the same argument lead to the bound here. Use the same argument. Then in particular, this is somewhat arbitrary in setting the value of c. You can also use another values of c. It doesn't matter. And we yield this bound. Finally, when the lambda satisfies this condition, we have this, and finally we get this bound. So the expectation of e, the power is lambda x, is less than this. So we complete the proof. So there are still two things to mention. The first thing is that, so why we have to apply this bound? This bound seems somewhat arbitrary and difficult to prove, although I asked this question in math stack exchange and have a good proof when people gives me a proof of this inequality. And here's another good proof. Let me see here. This inequality is somewhat more more intuitive or more beautiful. So this inequality can also be used here. So I write it here like we do not need to use such a sharp bound. You can institute 9/16 by 1. So this is more intuitive. You do not need to use such a sharp bound to prove the results. So the proof of this inequality is somewhat easier because you can directly use this fact and this fact, or you can calculate this or prove this inequality by the standard tool, like find the first order, second order derivatives, and then by some calculus calculation. So this also works. So you can use this bound and also apply this inequality and expectations. But here the range is somewhat different, but it will not have some impact on the final results. And you can also write these two cases, and you can establish different upper bounds for different cases, and finally you can get the results that X is also sub-Gaussian given the condition in case 4, given the implication the case 4. So the last question is how the inequality this comes from. I asked this question and some people give me a more intuitive proof. So let's briefly review what it says. So how to prove this inequality? This answer is correct. When y is larger than 4/3, it's intuitive and also true. When y is less than 4/3, the author also used this. So by applying this inequality, which is directly driven from the Taylor expansion, we get this. And in 2, we use this arithmetic and geometric inequality and get this result. And it's sufficient to prove that, so that the original inequality this is satisfied. Then since this is larger than 0, we only need to prove this. Denote left hand side minus right hand side by f, and we calculate the first order derivative, which is we get some range when it's larger than 0 or less than 0 on different intervals, and finally we get the critical value at 0 and 1/2. Then we can prove that f1 is larger than 0 for all y is less than 4/3, which is done. But I also have another question here. So how did this author River Lee come up with the solution? I don't know how he figured out this solution, but this solution is somewhat artful and arbitrary. It's somewhat ad hoc. So anyway, if you do not know this inequality is fine because you can use this somewhat not sharp one. This is 9 over 16 is somewhat sharp, but not the most sharp. The most sharp means the optimal how to say the optimal C here. The definition is here. So the optimal value of C so that this inequality satisfies is given by this solution here. Let me see. It's given by solving this, the maximized value of this. And of course, it doesn't have the closed form. The analytical value is here. C equals to 0.5574. And 9 over 16 is about 0.56, so they are close. So the Wainwright use somewhat sharp bounds here. But use this inequality is also okay. So what's the implication? What's the intuition? What can we learn from this proof? So the author, what we gonna prove here? We wanna prove that 4 leads to 1. So we have the condition like this, the e, but here the term is about the square of x, and we wanna get the here the exponential, the power is x. So how to get this solution from the quadratic form? From quadratic to linear, the author used this inequality. So here the power is quadratic and here the power is linear. And then by some calculation, we also split the range of s or the parameters in different cases. And the first case is somewhat easy to prove, and the second case you have to make some design. Here the author used the French-Young inequality. So let me see. To prove this, the linear form of the exponential, author used French-Young so as to incorporate the value of x, the quadratic form of x. So this incorporates the quadratic form of x, then we get the result from the assumption from case 4. Then we get the conclusion. So from this proof, we get some useful tools in proving different results. The first is about, let's make a brief summation. The first is how to firstly let me see this. So let me see. So from 3 to 1, here. So if x is symmetric, we can get the conclusion. But what if x is not symmetric? We can bound these odd moments in terms of the even ones. So this is a very important way to prove this. So we can bound the odd moments in terms of the even ones. And the second one is here. So how we incorporate the linear form and the quadratic form in the two sides of the inequality. So the author used this inequality. And of course, you divide the proof into different cases. Of course, the one of the cases is very simple to prove, and another one needs you to make some, special design. Is somewhat more complicated. And the next thing to mention is the symmetrization, where let me see. Red match. Red match. Symmetrization. Symmetric. Where? Symmetric. Red match variable. Electric. Red match. Here, a symmetrization argument. This technique. Symmetrization argument. Symmetrization. Here, the technique is symmetrization argument. Let me change the color of this. How to change the color of this? Okay. So we use the symmetrization argument here. And we bound the odd moments in terms of the even ones. How to add some colors here? Here. And the last one we can use this not so sharp inequality. Not so sharp inequality. Alright, so I just wanna add some color to this inequality, but not the use. Okay. So that's all. Thanks for attending today's lecture. Goodbye.